Good morning, folks. So Preben and I were just talking about this little booklet before we started, and I was just flicking through, having a look at the schedule from 2009. And one of the things that stood out to me was that these could be talks today. There's not very much that's just, some of the technologies have changed, but there's also stuff in here. There's one of the things that's talking about energy efficient cloud computing. On my YouTube channel, tonight's video is about energy efficient cloud computing, amongst other things. But there's a lot of stuff there, and these are the things that kind of interest me. What are those ideas that are durable? What are the ideas that are going to be true about our discipline in 50 years' time, and were true probably 50 years ago? And I think that there are some foundational principles that I'm going to talk to you about today, and I think that we should take them more seriously. And I think that when we do, I think that we can start approaching what we would think of as a genuine engineering discipline for software. And that's my theme for today. And I'm hoping to convince you that there's something in it. So I'd like to begin by doing that annoying thing that speakers do to liven up audiences after a party night. Would everybody please stand up? It won't take very long. And I would like you to think about how you think about your work. Now, I'm sure that given the nature of the GOTO conferences and this audience, that nearly everybody in this room at some point has been a programmer of some kind. If you're not now, I'm going to ask you to try and categorize yourself. So if you're not now, but just play along with the game and think about how you did think of yourself when you were a programmer, if that's what you are now. So there are different ways of us describing that. So we think some people may think of themselves as programmers, some as software developers maybe, some people as craftspeople. I've worked places where we had meme wranglers or something similarly silly. Or maybe you think of yourself as a software engineer. Right, so if you think of yourself as a programmer, would you please sit down now? Okay, if you think of yourself as a software developer, please sit down now. If you think of yourself as a meme wrangler, please sit down now. And if you think of yourself as a craftsperson, please sit down now. Right, so presumably the rest of you that are standing up think of yourself as software engineers. That's good. Now, my ambition, you can sit down now. Thank you very much for playing along. And my ambition is I would like at the end of my presentation that if we did that again, there'd be more of you standing up at the end. So who cares? Why on earth does this matter? Why would we be interested in this in any way at all? Well, I think that some of these things are more than only labels. I think specifically, given that my topic is software engineering, I think that the term engineering is more than just a label that means a programmer of some kind. I think that engineering, there's a bit more to it than that, and that's what I want to try and talk about today. So I'd like to explore the prospect of what is engineering and how do we think about it. What are the common foundational principles of engineering, and specifically how do those apply to software? And I want to end up by giving you what I think are 10 guiding principles that define or should define, do define for me, should define for you in my opinion, what software engineering really means and what it's about, and how we should apply that in reality, how we can apply that to doing real work. So let's begin with that first part. What is it engineering, and how do we think about it? I think in other disciplines, the simplest way to put this is that engineering is just the stuff that works. I'm talking about modern engineering. Engineering is an old idea. It goes back to a long time. The word is originally taken from building war machines, ballistas, and those sorts of things. Those were the people that were the first engineers. But I'm talking about modern engineering, the stuff that works. And software is one of the more difficult things, I think, that human beings undertake. So what's the stuff that works for us? It's important because we are building increasingly complicated systems, and those systems are increasingly serious. People's lives depend upon them. So what are the ideas that increase our chances of success? If we follow certain patterns of behavior, how are we going to do a better job? Because I think that's in other fields, that's what engineering is for. It's to give us those kind of guide rails. And I think that if we were able to find those ideas, this would be true whatever the nature of the software that we were developing. This is generic. This is not about specific technologies or specific languages or specific frameworks. I'm not going to be selling you a particular diagramming technique or anything like that. That's not what I'm talking about. So these ideas, you're going to recognize them all. Sorry, I feel like I'm doing some kind of dog and pony show and trying to sneak them up on you. I'm not. But these are kind of the foundations of our discipline. I've been talking about this kind of thing for a long time, several years now, and one of the things that happens to me is that I get involved in lots of conversations about bridges as a result. It starts with people coming up to me and says, yes, but software engineering isn't about bridge building. Well, no, it isn't. Of course it's not. And we don't, but I think we're probably doing what we often do, is that we're just miscategorizing bridge building as well. Bridge building, there is engineering in bridge building. The actual construction is, some of it's the engineering practice, but what I'm thinking about is different to that. And even if we think about the engineering in physical devices, the engineering in car building is different to the engineering in bridge building. And the engineering in chemical engineering is different to the engineering in aerospace engineering. So we can learn things from these different disciplines. There are some common themes, but one of the things that we can be sure of is that if we were to discover an engineering discipline for software, it will be ours. It will be unique to us. It will be special for software. It's going to be different because software is different to other things. I'm going to be pulling some examples from aircraft engineering, space engineering, and car automotive engineering, just to kind of pull out the threads. And a little bit about Lego as well, but we'll get to that. So what does this really mean for us? What can we learn from these other disciplines, and how can we kind of apply this and do useful things with it from a software point of view? I think one of the things that's thinking about is how we think about what engineering means. And this is my working definition that I like to use. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. And all of those words matter. That's about as concise as I can get and get all of the ideas in that I think are meaningful in this context. I'll keep reminding you, I mean modern engineering, not the kind of practical folk art of engineering which it came from. I'm talking about post-scientific revolution engineering, the practical solution of problems, because we're looking for the stuff that works. To put it more simply, engineering is how we solve the hard problems, whatever those hard problems are. And I think we dismiss it at our peril, because this is how we solve the hard problems. Engineering is the foundation on which our high-tech society is built. And I think it's hard to refute that. If you look at the data, human civilization has been around for a very long time, but didn't change very much for a very long time. The impact of engineering on our society is huge. Here's a picture of the average per capita GDP in the world from 1000 AD to 2000 AD. And you've got this kind of power curve, this hockey stick. This is where science started. Here's another picture of technological advancement, and this is the rate at which innovative technical things have been built. And you can see there's this massive clustering towards the end. This is where science happened. And here's a graph of a range of different things. Life expectancy, GDP again, war-making capacity. Not all of these are good things. And the number of people living in a democracy and so on. And once again, this is where science started. This is the stuff that revolutionized the way we exist as human beings. This last picture is just staggering. This is the rate of doubling of all human knowledge. At the start of the 20th century, all human knowledge was doubling once every century. By 1945, it was doubling every 25 years. Today, the estimates are that it's doubling roughly once every 11 or 12 hours. That's the rate of advancement that we're talking about. So science was way back there somewhere, and this is when software started. So the impact of our ability to learn and do these things is severe. And as I say, I think that I think it's a reasonable statement. I don't think it's overly ambitious to say this is down to the application of solving problems with that scientific, rational approach and knowledge. This is how we do the hard stuff. We are a species that has evolved to learn things and wield tools and use knowledge. So I would think, if I'm honest, I think the height of creativity is engineering. It's not painting a picture, because painting a picture you can do anything. There's no constraints really for that, other than aesthetic. If I want to do an engineering version of painting a picture, there's got to be some utility to it. There's got to be some way in which it works, and it's more constrained, which makes it more difficult and more creative. I would put something like putting a rover on Mars as the height of human creativity. That kind of thing is the sort of stuff that I've got in the back of my mind when I'm thinking about this. So let's start moving on and start thinking, what is engineering really for? And I think it's not often what we think about it. It's not about defining a solution. It's not about saying, there's your target. It's not that at all. It's actually about ruling out stupid solutions. Look at all of these pictures. It's about now saying, don't do that, that's stupid. So you're narrowing the range of possible solutions into a spectrum of good solutions. And then you pick which ones you want. So this isn't about some kind of cookie cutter process where you're just going to churn a handle and spit out something great. You're going to need that ingenuity and that creativity to be able to do something great. But if we take an engineering approach, we can say, well, we definitely don't want to do that because that's dumb. And therefore, we kind of narrow our field of search for good solutions. The other way in which we often get this wrong is thinking about engineering as the kind of production lines. The first thing to say is that the churning out of the cookie cutter approach isn't the engineering. Designing the machinery and the process in the first place was the engineering. That's the creative part. That's the part that I'm talking about. And the other thing is, this isn't our problem. This is nothing to do with us as software. One of the things that's different about our stuff is that our product is software. This is never our problem in software. If you think about what it is that we do, we're going to write some code. We're going to, at some level, we're going to generate a stream of bytes that represents the system. However big or complex our system, we can represent it as a stream of bytes. And one of the unique characteristics of software systems, any digital artifact really, is that we can clone it perfectly, essentially for zero cost. At such a low cost that it's negligible anyway. So at the push of a button, we can reproduce entire systems for free, so we never ever have a production problem. And yet I would say that a large part of the last 40 years has been spent trying to make our problem a production problem. Wrongly, that doesn't work. And so we're all here, we've been talking about agile things, and the reason that stuff's important is because that kind of more exploratory approach to discovery and learning is a much better fit for software than trying to create some kind of cookie cutter problem, which is solving something, a problem that we don't have. So if you think about what a waterfall approach is, it's a production line for software. Production lines don't fit our problem at all. So, engineering is about exploration and discovery. And we should be optimizing for that. Software development is about exploration and discovery. We don't know what our customers really want. The customers don't really know what they want. We don't know whether our solution's good. We don't know whether our design is going to be a good one in the long term. Is it scalable enough? Is it resilient enough? We don't know any of those things. But we learn those things, and we build on that learning. I think one of the key foundational differences between the more traditional thinking and the kind of thinking that I'm talking about is that in more traditional approaches, you start off needing to know everything that you need to know in order to be able to build your production line precisely. And what I'm talking about, so you start off assuming that you're right. In my worldview, that's completely stupid. I start off assuming that I'm wrong, and I want to find out as quickly and as efficiently as I can where I'm wrong so I can learn and correct the wrongnesses. And that's what I think of as a much more scientific, but also a much more engineering style of approach. So let's start thinking about the stuff that works. And I think that if we want to start thinking in these terms, as engineers, then we must become world-class experts at learning. That should be at the core of our discipline. We should adopt the techniques and the skills, learn the skills of becoming expert at learning. And that's, one of the places to start. But also, we build these incredibly complicated systems, the most complicated systems that human beings build. Think about the World Wide Web as a system. That's the most complicated thing on the planet, with the exception of, a collection of human brains, perhaps. But that's the most complicated thing on the planet. So we also need to be able to find ways of managing that complexity. So in addition to becoming experts at learning, we need to also optimize for managing complexity. We need to become expert at that as well. And those are the two foundations on which I think an engineering discipline for software should be built. I've got 5 ideas in each of those categories. These are the 10 ideas in total that I started out talking about. And for optimizing for learning, these are the 5 ideas. So let's explore each of these. Let's start with iteration. You can think of something like the evolution of the aircraft as starting as a craft-based system. That's not quite right. The Wright brothers were actually pretty good engineers. They did some foundational work and added to the research on the aerodynamics of flight. They were the first people to build a wind tunnel, for example, and scientifically measure different wing profiles. But still, it was built out of spruce and covered in fabric and painted banana oil on the top to make it windproof. It was pretty crude by modern standards. They were also death traps. The early aircraft killed a lot of the early aviation pioneers. They were incredibly dangerous things. But through iteration, on a long cycle, but by taking an engineering approach, you don't start off with a perfect answer. You build something that works. This is the Wright Flyer, flying less than the wingspan of a Boeing 747 in its first flight. But you build something that works, and then you find out where you're wrong, and you correct that, and you correct that, and you improve that over time. This happened in aviation. We started building safer aircraft that could carry passengers, and they could fly more regularly, until we get to the kind of passenger air transport that we've got today. In 2017, the equivalent of 2/3 of the population of the planet flew in a commercial jet, and nobody died as a result of an airplane accident. That was the first time that had happened. But that level of safety was achieved through this iterative approach to engineering, trying stuff, seeing what worked, figuring, and sometimes this learning is written in blood. There were accidents that killed people. We learn from those accidents. We say they're never happening again. It's one of the reasons why Concorde was stopped, because they wouldn't have designed where the engines were in Concorde these days, because they'd learned since the design of the aircraft. That's how engineering proceeds. Iteration is an interesting idea. If we think about this just in information terms, what's iteration really about? We're going to have a goal of some kind, or a target that we'd like to hit. And what we need now, we're going to have a starting position, which isn't at the goal yet, obviously. And what we need to be able to hit that target, if we take an iterative approach, is just a fitness function. We need to know whether a step that we take is closer to or further from the goal. That's all we need. We don't need any more than that. And then, even if we just made stuff up and just headed off in the wrong direction, as long as we used our fitness function to determine whether we're closer or further from the goal, we're learning. And ultimately, we will hit the goal. There's kind of no argument with this. This is a more powerful way of achieving the goal. This will work even if we change where the goal is. We just make step by step by step. We try stuff out and say, yeah, that didn't work. No, that's not a good idea. Let's not do that anymore. Let's do this thing instead. Oh, that worked. That got us closer. And then let's try this other thing. No, that didn't work either. That's how we do real engineering, how we do real learning. So working iteratively is really, really important to be able to give us these opportunities to learn, to evaluate what our ideas are and to make progress. The next idea in my list of 5 for us to focus on in terms of optimizing for learning is feedback. And in this kind of picture of iteration, the feedback here is our score in the fitness function. The fitness function can be anything. It can be anything that determines whether we're closer to or further from our goal. It could be sales or, I don't know, latency or whatever it is that you care about. But we use that. And by iterating, we make progress in smaller steps, and we give ourselves more and more opportunities to learn and to evaluate, to gather feedback, to understand the implication of our choices. Another kind of practical example, I got chatting to Preben and forgot I was going to do this. I was meant to get a real broom and show you with a real broom, but I've got a little animation instead. So how do you balance a broom? Let's imagine that we're faced with the problem of balancing a broom. Well, we could try the waterfall approach. We could try figuring out exactly where the center of mass is of the broom, and then we could very closely inspect the handle of the broom and figure out what's the point of contact of that handle when we're going to balance this, when the center of mass is directly above that point of contact. And then with great skill and precision, we could maneuver the broom to the point where the point of contact on the floor is in line with the center of mass precisely, and we've managed to very, very skillfully not allow any impulse so that the broom's moving one way or the other, and then we could balance it like that. What are the chances of that working? Very, very, very slim, because there's only one answer. Realistically, there's one answer to that problem. The more realistic way, the thing that we'd really do, is we'd just put the broom on our hands and we'd start wobbling our hand around. But that's based on feedback. We look at the way that the broom's tipping and we say, oh, it's going over there, I'll do that instead. And that will work. And the faster we move our hand, the smaller we need to move it. The faster we iterate, the smaller the feedback is, the corrections need to be. And that works even if I was balancing a broom and Jessica came up on the stage and shoved me, so I staggered around. I could probably still balance the broom. I'd have to do a big move, but I'd still be able to correct. That's the power of feedback. And this sounds, just picking up the broom and putting it on your hand and wobbling your hand around sounds like a less formal way of doing things, but it's not. That's the more powerful, more correct way of doing things. This is how space rockets work. Space rockets have gyroscopes in them, and they detect how the space rocket tips, and they vector the thrust to precisely balance the broom on the thrust of the space rocket. So this is an incredibly powerful idea. Feedback is one of those ideas that's at the heart of nearly every control system in engineering of almost any kind. The next idea is the idea of incrementalism, working incrementally. This is a picture of the first module of the International Space Station. And then, over the years, they added more and more modules, and they built it up to the remarkable device that's been in orbit now for years and years and had astronauts living in it all of that time. It didn't start out. They had a rough plan, but the plan changed over time. They evolved as they learnt more, as they found out where they were wrong. This is how real engineering progresses. This is how science progresses. This is what we do. The other way of thinking about this, on a slightly different time scale, is looking at something that's a bit closer to our experience, of something like an iPhone. This is the first iPhone, and this had no third-party applications, no GPS, no video, no FaceTime. It was revolutionary. Phones didn't look like that when it came out. And I'm sure that when Apple released this, they were thinking, oh, one day, maybe we could put GPS in it. But they won't have planned it. They won't have had it in detail. They might have had some fond ideas about where it might go, but also there'll be thoughts that they never thought of. They probably didn't think of Siri necessarily at that stage or whatever else. I think this is an iPhone 4S. This came a little bit later. This was a 3G phone, so it had no 4G, no Siri, no face recognition, no Apple Play. But incrementally, they added new features. That's how we evolve products until we get to something like a modern phone that is, ridiculously powerful cameras and LiDAR sensors that can map things in 3D and all kinds of stuff. That's how real engineering works and allows us to make progress. But one of the things that is necessary for that to happen is the ability to change things. In this case, they're kind of reinventing the thing all of the time, following some sort of form factor. There's probably no reuse of components very much going on here, but sometimes there is, sometimes there isn't. But certainly, that ability to change things is important. The next in my list is the idea of working experimentally. And I think that we probably think of this as being quite a scary idea. Some people, certainly some organisations say, oh, we can't be experimental, we can't afford to be wrong. Well, if you can't afford to be wrong, you can't really afford to do anything. How do you make progress if you're not willing to take a risk and make a mistake? If you come up with an idea and you predict some sort of perfection of an idea, and your experiment or your trial proves that you were correct, what have you learned? You haven't learned anything. So the superpower of science as an approach is that we learn more when our experiments go wrong than we learn when they go right. So being willing to be wrong is a really important idea. The trick is to be able to do that in a controlled way so that it's not going to hurt you if you do it wrong. And that's what an experiment is. So organising our work to be experimental is really important, and it allows us to proceed more quickly with greater surety, more safety, and still allow ourselves to be wrong. Allowing yourself the freedom to be wrong, I think, is probably one of those kind of ground state rules that underpins the idea of science and engineering. Because we're starting off assuming that we probably are going to be wrong. In order to be able to limit the blast radius, we need to think about ideas like controlling the variables, and that's a key to working more experimentally. Again, an example from aviation. For decades and decades, the way that aviation made progress was there was a kind of rule. I was going to say an unwritten rule, but I think it was written down. But there was a rule that you don't fly a new engine in a new airframe. So the way in which you build a new aeroplane is that you start off with an old aeroplane and you take the engine off and you put a new engine on it. And you go flying that because you've got a proven platform. You're limiting the variables to the engine. You know that the airframe's okay, so you'll try it out and you'll see how that goes. And in those days, before computer simulation and all that kind of stuff, that's what they do. And then what you'll do is you'll get the new airframe and you'll bolt an old engine onto it and you'll fly that for a bit. And then when you've tried that out and everything looks okay, you put the new engine together with the new airframe and you've got a new airplane. That's how you make progress. You control the variables, you try stuff out, you learn, and you say what works and what didn't, what killed the pilots, what didn't, and make progress. The last in my list of 5 is being empirical. And my brother-in-law Bernard is in the back of the audience over here. And he's a scientist. He did a PhD in physics. And we had long arguments about the philosophy of science and whether I should include this idea as well as experimentalism. And I wanted to in the end, and I did. I kind of overruled him a bit after long debate, for which I was very grateful. But I think that empiricism is probably the thing that differentiates engineering from science, because this isn't just about pure theory. You could argue this about real science as well. You need the experiment to prove what's going on. But certainly in engineering, it's a practical discipline. It's a pragmatic discipline, and so we need to understand the impact in the world of our ideas. Following on with the aviation theme, this is a real aeroplane, and this had gone through the development. This is a German jet from the Second World War. This is a Heinkel, and this went through the kind of phase that I was talking about. There were versions where the airframe was tested with a propeller engine, and they flew jets on older airframes. They did all that stuff, and then they built this thing. They put all the pieces together, and I think this is a really nice example of empirical learning. I want you to pay attention to the undercarriage. This is what pilots call a tail dragger arrangement. The small wheel is at the back, which tilts the whole thing up. And the reason for that is to give lots of room for the propeller on the front so that it doesn't hit the ground. You can have a big engine with a big propeller and it doesn't hit the ground. And so they were used to building airplanes like that, so they built this jet engine like this, and then they went testing it, and it melted the runways. It destroyed the runways. So now, if you look at a modern jet engine, it's got the little wheel at the front. The two wheels are kind of further behind the center of gravity, so it stands like a tripod, and the jet is more horizontal, and it doesn't burn the runways. So there's that kind of practical learning. We're going to get things wrong, so we want to learn from getting things wrong. Here's a more modern example. This is the Starship being built by SpaceX. This is the spaceship that's supposed to be able to take people to Mars one day. The first fully reusable spacecraft is the Ambition. And as you can see, this is one of those points where the Ambition kind of failed a little bit, but this was actually a success. This was a flight up to, I think it was 20 kilometers, this one, and it just didn't nail the landing. It blew up on landing, but they learnt loads from the flight, and then they learnt loads from this as well. And the next flight, they actually landed it. It still caught fire on the next one, but this is how you learn. This is how real engineering progresses. It's not a cookie-cutter process. It's a process of trial and error. Moving on and starting thinking about the complexity of the systems that we build. Modern software is ludicrously complex. In some, the Amazon picture here, those are microservices and the communications channels between microservices. And if you really saw this picture, this is dynamic in real time. It looks organic. This is a complex thing. This is not something that you can just kind of wrap your head around and just nail and understand clearly. Modern software is complicated, genuinely so, and complex. Software, just for the Canadian people in the audience. Software development is about learning and it's about managing complexity. So I've got another 5 things about managing complexity. And once again, these are ideas that you're all familiar with. One of the things that I would like to remind you, I'm not just saying, remember modularity or iteration's good. I'm saying these are tools that we could and should prioritize above all other things. That's what I'm saying. We'll come back to that maybe. So let's look at each of these. Modularity is about building systems, compartmentalizing the systems that we build. Again, we can kind of learn lessons from other forms of engineering. We build things to be maintainable. In this case, we can take the engine out and we can work on the engine and maintain the engine separate from the rest of the aircraft. We can replace this engine with a different one if something more efficient comes along, or you wanted a different pattern of use for this aircraft. So modularity gives us more flexibility and more use in our designs. Even very tightly cohesive systems like a modern phone are still modular. There are components of the system that have distinct separate jobs. And that's important, to be able to wrap your head around the notion of being able to build something as complicated as these kinds of systems. More in our kind of wheelhouse, When I first started programming in the 1980s, if you wanted to print something out on a printer, you had to know which printer you were going to be talking to, and you had to write the code to talk to that specific printer. There was no concept of a printer driver in the operating systems that I was using at the time. And then later, the idea of a printer driver came along. We got an abstraction of printing, and then we got a module that we kind of plugged in behind that abstraction that decoupled the whole thing and allowed us to kind of generalize the idea of printing so that our word processor application or whatever else it is didn't need to understand the guts of how our printer worked. That's a good thing. Here's some code. This is not very modular code. This is code that I use quite a lot to poke fun at because it's not very nice code. This is 361 lines in an if statement, and it's written in C, but just because it's written in C doesn't mean you have to write crap code. And this is what that looks like in context with this function. It's a fairly horrible long function. It would definitely have failed Adam Thornhill's test. This is red code on his model. It's nasty, but I think that you could improve this with a fairly small, simple step. I think if I read this correctly, what this is really saying is it's saying, if there's no connection, make a connection. And if I do that, what I've done is I've just made the code more modular. And now I could deal with each of those pieces in different ways. I could maybe reuse the idea of creating a connection in other parts of the code. Looking around at this in context, there were lots of other horrible pieces of code that looked really quite a lot similar to this. So I get more reuse, more flexibility, more ability to compose things in different ways. Gives me a huge win if I can start to compartmentalize my code and treat that as an important thing to do. Treat that as something that I'm always going to do. My favorite description of what good design is from Kent Beck, and it's this. Good design is about moving the things that are related closer together and the things that are unrelated further apart. I think that's a pretty good description of what good design is about. And you can think about those as two ends of the spectrum. On the one hand, we've got modularity. That's about moving the stuff that's unrelated further apart. And on the other hand, we've got cohesion. That's about putting the stuff that's related and changes together. And that cohesion is the next one on my list of principles that we should be using all of the time to guide our design and coding decisions. Next is separation of concerns. And I learned this, I think I knew this before. Well, no, I certainly knew this before, and it was certainly an aspect of my style. But this got hammered into me more by my friend Martin Thompson, who's at the back of the room. Martin is one of the best programmers I know, and he's got this laser focus on separation of concerns. And immediately, if he's looking at any piece of code that he says, oh, that's doing two things, I'm going to rip that out, I'm going to rip those things apart. And each piece of code, he's focused on one job. That makes it easy to work on. It makes it simpler to understand. It makes it more modular. It gives us a good guiding process that allows us to deal with the complexity in the system and drive us towards more modular and more cohesive code. This is a modern electric BMW. And this is a good demonstration of separation of concerns. This is built on this platform. This is their new EV platform for electric cars. And they've separated the concerns of transmission, steering, batteries, charging, all of that stuff from the utility of the car. The shell that represents the car is replaceable. So we've got this one platform, and then whether you want an estate car or an SUV or a sedan or a sports car, they're all built. They're all going to be built on the same platform. So separation of concerns gives us this freedom. It gives us this clever way of being able to think about different parts of the system and concentrate on the bit that's interesting for us in this particular context. It gives us more focus and it gives us more clarity in the way in which we can kind of do things and make progress. Another idea, here's another car, is the idea of abstraction.
In the early days, this is obviously very clearly a very, very early car. And there wasn't much abstraction going on here. This stick here, I think that this is both the accelerator and the brake in one big lever. And if you look, I tried to look carefully to see how that was working. I think that's what's going on there. There's also this bit, which I bring to your attention. That's how you do steering, and that's a kind of tiller thing. And you can see how that works. You can see the linkages. So there's not much abstraction going on here. What happened with the evolution of cars was we started to increase the abstraction. So we start off looking at, somebody came up with the idea of a steering wheel, and the one on the left there is, it's still fairly old-fashioned, but eventually we get to something like this, and that's a modern steering wheel, which is actually an extremely abstract device. How does that work? I guarantee you that you can't tell me, because you can't tell from there. It could be that there's some kind of mechanical linkage. Maybe there's something like this, a parallelogram steering system or rack and pinion steering system. And that's the way that it works. Some cars work like that, and they all have steering wheels. Or maybe it's a more assisted system. Maybe it's a power steering system and there's hydraulics involved and we're controlling those. Or maybe it's a modern car and it's purely electric and we're just sending signals and that's being processed by a computer of some kind and then driving actuators to move the steering. It could be any of those things, but the problem's being abstracted away. And that's important. That gives us the ability to build complex systems where we can interact with other parts of complex systems and not care about how they work. Because we've got an abstraction that's shared. So I can interact with something over there and I can be very clear about the ways in which I'm interacting with that thing over there and still not care at all about how it works. That gives us an awful lot of freedom to be able to change things. It allows us to make changes in one part of a system without worrying about what's going on somewhere else. Let's look at that in the context of code. So here's some code. Where are we on time? Here's some code, and this is not very abstract. There's an awful lot going on here. We've got a nasty back channel to the database. This is not going to be nice code to work on. We could try to do better. We could instead try and raise the level of abstraction perhaps and simplify the nature of the interactions and be a little bit clearer about what's going on instead of all of that detail. We could do something like this. We could say place an order and then respond as an order is placed. Now we've got an abstraction and we could change one side of this piece of code without worrying quite so much. And that's important in terms of the impact of where we design. The way that we design these sorts of places in our code are more important than other parts of our code. So we should spend more time worrying about things like abstraction and the protocols that we use for conversations at these points. Our code needs to keep secrets if we want to be able to retain our ability to change it. The last in my list is the idea of coupling. I told you there was Lego. So when I was a kid, I used to have Lego like this. I still like Lego like this. I've got some lovely grandchildren and I like playing Lego with this. We can build buildings and submarines and spaceships and cars and whatever our imagination's like with bricks like this. My little granddaughters can do it any way they like and they can reassemble it and say, oh yeah, that's a lovely pig or whatever else that it is that they're trying to build. Even if it doesn't really look a lot like a pig, that's fine. This one is kind of different. It's not bad, it's just different. The coupling here is deep. I can't really make a submarine out of this because the parts it's the wrong set of parts. And there's one way of putting these together so that they make the kit. So it's a very, very different kind of system. So coupling matters in terms of the utility of our system, the flexibilities of our system. So it's not always about loose coupling, but I would say that managing the coupling of our systems is very important with a tendency towards preferring as loosely coupled as you can sensibly get away with in your context. Simple example. So here we've just got our two systems again, and we've just changed the date format in the orange system on the right. In the first example that I showed you, this is a bad thing because we're just exposing all of the internal workings of that system, really, and we've just broken that system, which means that the whole system's broken because they were all deeply coupled. In the second system, because of the separation and the more abstract interactions, we've got a chance. Because what we could do is, we know that we want to change this implementation, so let's build a little facade, a little adapter, a little translation point into our system. So now, when we issue an instruction and say place an order, and we want order placed back with a version 1 date, our little translation layer here can just translate version 2 dates into version 1 dates. And maybe we had 2 of those, one for a version 2 of the API, one for a version 1 of the API. But managing the coupling in this way, again, gives us more freedom of movement, more ability to change and maintain our systems. Managing complexity, these are the 5 things again. And I want to say again, this is more, I know that you know all of these ideas, but what I'm saying is that whenever you have a choice in software design, I would recommend that you aim to try and make the choice that improves the modularity, cohesion, separation of concerns, abstraction, and coupling, getting that appropriate. Because I think if you do that, you're going to end up with better systems. This is not just motherhood and apple pie. These are tools that we can use to rule out some of the stupid decisions. Instead of just doing the practical thing, the pragmatic thing is saying, I've got this 360 one-line if statement, and I've got to change it, I'll just add this piece of code in here because I happen to be here at the time. No, I want to have a model of the system, I want to organize the system, and I want to improve the system. These are the tools that allow us to do that. A simple example. So here, I'm going to whiz through this quite quickly because I'm running out of time. But here's a car, and this car has a petrol engine, and it's got a start method. So when we start the car, we're going to put the car into neutral, apply the brakes, and then we're going to start the engine. Okay? So let's write a test for this. Are we going to create a new car? We're going to say start, and damn, there's nothing that I can do. I can't really test this. I could try breaking encapsulation and go and look at the private state of that engine inside, but the programming gods would definitely punish me for that. That's not a good idea. So this is not testable code. This is not good. So let's just look at this from the point of view of improving the testability. This is one of the tools that we can use. I'm not going to go into that in much detail, but striving for testability helps us to improve the modularity, cohesion, separation of concerns, all those other things. So let's just look at that. So here's a better car. Let's start looking at that. We're going to start with a test, and should start better car engine. And the thing that I'd like to be able to do really here is check that the engine was started successfully. So I've just started designing. Did you notice? This is an iterative approach to designing. I'm getting feedback here from saying, well, from my design, if it looked like that, I'd be able to test. When I start that, well, I want that to happen when I start the car. So I'm still designing, and therefore, I'm going to need to hold on to the engine. So I'm going to use dependency injection. I'm going to pass the engine in as a parameter in the constructor for my better car, and I'm going to use a fake engine. This is what my fake engine looks like, just so you can see. I'd probably use a mock if I was doing this for real, but it just says, yes, you started. Now I've got a working test. I've got code that is better. It's very similar to the code that was there before. The only real difference is that little change in the dependency injection driven by my desire for testability. But think about what that means in terms of the modularity of the code. This code is more modular because it doesn't know how to create a petrol engine. It's thrown that away. It's more abstract because it's dealing with engineness rather than petrol engineness. It's more cohesive because all of the stuff here, to the degree that it cares about, is about car. and not about it. There's less about engine here, and it's less coupled for the same reason, and we've got better abstraction because we're dealing with an abstraction of engine rather than, so all of those properties that I just talked about were enhanced by just following fairly stupidly, fairly dumbly, the line of test-driven development. That's the kind of advantage that we get from engineering. Following a practice that, whatever our level of skill, would tend to enhance the quality of the output. It's a thought, isn't it? What this means in practice, when we end up, is in production, I can do exactly what I did before. I can have a car, go on. I can have a car with a petrol engine. I can create that exactly the same as before. Or I could now have a car with an electric engine, and I haven't changed my code, so my code's more useful, it's more flexible, it has wider utility. It's simpler than it was before. And if I was some kind of crazy person, I could build a car with a jet engine if I wanted to. All of this is just better code. This is just better code as a result. So here are my 10 things that I think should represent the principles, the foundations on which we build our discipline and operate our discipline. I think that if you always, whatever choice you are faced with, whatever technology you're working in, worked to maximize iteration, feedback, working incrementally, working experimentally, and doing empirical discovery, and you preferred solutions that were more modular, more cohesive, better separation of concerns, more abstract and reduced coupling, you would increase your chances quite dramatically of getting a better outcome. Just for a moment, imagine two systems. One of them, you're not going to do any of the things over here, okay? So you're not going to iterate, you're not going to gather feedback, you're not going to experiment. So what you're going to do instead, well, you're going to think really, really hard, and you're going to come up with the perfect solution, and you're going to know exactly what's involved in that perfect solution, and you're going to execute on that perfectly. What are the chances of that happening? That's standing the broom up, as we described before. Or we could do all of these things. And now think about the things over here. Imagine maybe a piece of software that you work on and know very well. Imagine two versions of that. One of them has no modularity, no cohesion, no separation of concerns. It's all one big mess of code. There's no abstraction. Everything's really coupled and gnarly. This is so common that we've even got a name for it. This is what we call a big ball of mud. These are real systems. And now imagine a piece of code that's modular. Every piece that you look at is doing one thing. It's got good separation of concerns. It's cohesive. All the stuff that you need is in that one place, so you can see it clearly. Where it interacts with other parts, it's doing it through abstraction, and so you can clearly see those interactions and you can understand them. And largely those tend to be on the more loosely coupled side, so you can make changes in one place without worrying about that affecting everywhere else. Which version of the code would you prefer to work in? I guarantee you it's the second one. And please notice, I have said nothing at all about technology, tools, frameworks, methods, anything else. I think these things represent an engineering discipline for software. I think that if you were, for some strange reason, to follow my advice and just work this way, you would get better outcomes. Whatever it is that you're doing, I think that's true. And I think that would be the kind of property that we would expect from a genuine engineering discipline for software. These things matter for one reason. And this is a thought that I would like to leave you with. They allow us to change our software. They allow us to do it with confidence, safely, quickly, efficiently. So, I thought that Kent Beck was a genius for a long time when he subtitled his book, Embrace Change. I didn't get it for a long time. Change is a constant. Everything changes. Our understanding changes, requirements change, plans change, JavaScript frameworks change all of the time. Change is just a feature, just suck it up. There's no point fighting that, that's just the truth. And to work in an environment where change is so pervasive, so constant, we have to adapt for learning. We have to take on the discipline that we're going to start off assuming that we're going to be wrong and find ways that we're wrong and correct the ways in which we're wrong incrementally, iteratively, and work to reduce the coupling in our systems and improve abstraction and modularity. This is the idea that I would like to really leave you with. I would argue that the quality of our system is defined by one thing pretty much, the ability to change it. Of course, there's lots of other things that are important. But if you can't do this, you can't get those things. You can't make it faster, you can't make it more resilient if you can't change it. You can't make it better fit for customers if you can't change it. So working to retain our ability to change our code is the foundational principle, in my mind, on which we should build an engineering discipline for software. Thank you very much.